Okay, lecture number 17. We're going to be talking about, this is actually a bit of a strange lecture because I haven't found a great way to put it together. There's like 3 different things that we cover and then we tie them all together at the end. So we're going to be talking about Markov decision processes. Has anyone heard about those before in another course? Okay. Then we're going to be talking about continuing tasks, which are tasks that don't break down nicely into episodes. And then dynamic programming. I'm sure all of you have seen some sort of dynamic programming before. Anyone? Maybe not at the algorithms course yet, but yeah. We're going to be talking about how to solve for the value function using dynamic programming. So all of these things are seemingly unrelated at first, but then we'll end off by tying them all together with some nice math. And whenever there's math, there's exam questions. So just keep in mind when you're watching this that anywhere I've done a sample calculation, that is a very good type of exam question for the final. Like here it is with different numbers, solve the same sort of thing. So first let's talk about Markov decision process, or MDP, if you've heard it called that before. Before we talk about that, we need to talk about what the Markov property is, and Markov is just a name of the person who discovered all of this stuff. So in the reinforcement learning framework, agents make decisions as a function of the state of an environment, right? That's what we've been talking about so far. You have some sort of decision function, it gets passed in a state, and out pops an action. So just recall that the state of an environment is whatever information is available to the agent at some perceptual instant, right? Like if I took a picture of this classroom, that would be the state of the classroom right now. If a state contains all of the relevant information for making a decision, it's said to be Markov, or to have the Markov property. And so intuitively, this means that if there's no state history required, we talked about this all the way back at the beginning, then the Markov property holds. So for example, if we're playing a game like checkers or chess, where there is no hidden information, and we can make the optimal move just by looking at the current state of the board, but we don't need to know what the sequence of actions that got us here is. So for example, in Connect 4, that would have the Markov property, because I can just look at the state and make the best move. I don't need to know what stone was placed on what piece first. It doesn't matter, right? But in some cases, it does matter, and we looked at this example back in one of the first lectures as well, where this guy playing League of Legends over here comes in and snipes the last hit on this objective. But from his point of view, it looked like this, right? And so he had to combine a whole bunch of knowledge that he has about the game, combined with the state history going back possibly even a few minutes into this game in order to take this shot at the right time. Now that doesn't mean he was guaranteed to make that shot, right? This is still like a low probability of happening, but this is not, this is a case where the Markov property doesn't hold, because he would have had to know, 30 seconds ago they started attacking the Baron and they have these items, or the last time I saw them, etc. So the Markov property does not hold for all environments, just for simpler environments. So if we want to define it a bit more mathematically, so in general, environment states and rewards may be dependent on the complete action sequence, right? So what this means mathematically is that, so I'm going to use PR here for probability. And so the left of this bar is what's going to happen, and to the right of the bar are the things that it's dependent on, right? So here it says the probability that the next state is a given state, and the next reward is a given reward, is dependent on the complete action history to date, right? So this is that League of Legends example. The probability that the Baron was going to die to this shot is dependent on all the things that have happened so far in order to make that decision. However, if the Markov property holds, then environment response at t+1, and environment response meaning whatever the state and reward is going to be, depends only on the state and action at time t, not the entire history so far. So this simplifies things dramatically by saying that the probability that the next state is S prime and the next reward is R is only dependent on the state that you are at and the action that you took. You don't need to rely on the complete action history. So then the Markov decision process means that any RL task that satisfies the Markov property is called an MDP, or a Markov decision process. And if you've ever, you've probably, not you, but if you have friends in engineering, this is a big thing in engineering, is Markov decision processes as well. So if state and action spaces are finite, finite meaning, you know, we've got some limited number of things that we can do at each state, like a chess game or something, then this is called a finite MDP. And MDPs can also be used in partially observable environments. And so partially observable Markov decision process is called a POMDP. So that's why that's called that. So let's define a Markov decision process then. And this will be, you know, a great exam question, like knowing what all of these things are. So here an MDP is defined by 5 properties. And so S, A, P, R, and this looks like a Y, but it's a gamma. And so what how I remember this is I say in my head SAPRI, because I don't want to say SAPR gamma. But if you've ever on an exam got to recall what the 5 things are, I just SAPRI, and then you can, oh, I remember what those letters sort of mean, so I can write it down from there. So S is the finite set of states that you're working with in the environment. So this is all the states that are possible in the environment. A is a finite set of actions. And within A, this is like the set of all the actions that are legal at all the different states. So AS would be legal from state S. This one here, PASS prime, that is the probability that taking, sorry, I'll go over here. So the probability that the next state is a given state, given that you took this action at this state. Okay? So for example, Markov decision processes can deal with randomness. So if we're talking about a game of cards, like blackjack, for example, if I have 20 and the dealer has a 6, and I take the action of hitting, what is the probability that the next state is a winning state? Right? So that is, it's not a fixed well, it's not set in stone that I'm going to win with that hand because the cards could come out in a different way, right? But any environment in which you have a deterministic environment, so there is no randomness, then the probability of going from this state to another state with a given action is always 1, right? So that would be 1 if your environment is deterministic. RASS prime, that is the reward after transitioning from state S to S prime via A, right? So again, so far you might hear people like me in the past saying that I got a reward from doing this action, right? So I'm at a given state, I do an action, I get a reward. But to be fully complete, what you actually get the reward from is not just from doing an action, but which state do you actually end up in, right? So again, that blackjack example, well, I was at a given state and I took an action. The reward that I get is also dependent on did I win or not, right? So did I end up in the winning state or did I end up in a losing state or a drawing state? So the reward depends on that. So it really is a combination of these 3 things. What state did you come from? What state did you end up in? And what action did you take? Based on those 3 things, here's the reward that you get from doing that. And then gamma is a value between 0 and 1, inclusive, which is called the discount factor. And I'll explain what that means in a couple of slides. So the MDP problem, or objective, is to compute a policy pi that maximizes the sum of future discounted rewards. Okay, so the sum of rewards, that's the return, but now what we've done is we've introduced this discount factor called gamma. So what does that discount factor do? So discounting, so the agent's trying to select actions that the sum of discounted rewards is maximized. Okay, so if you look in here at this formula, k equal to 0. What's anything to the power of 0? 1, right? So if you look at this summation and you look at this here, so this summation typed out term by term is this up here. This is the return, right? So if it starts k at 0, then gamma to the 0 is a 1. So we multiply our first reward that we get by a 1. The second one, k equal to 1, then that will just be gamma, right? So RT plus 2 is multiplied by gamma. The third one will be gamma to the power of 2, so that's gamma squared, and so on and so forth, right? And so the reason it's called a discounting factor is that if gamma is between 0 and 1, then this goes down and down over time, right? So just picture gamma is 0.5. So what will happen? Well, if gamma is 0.5, then our return is going to be the sum of, okay, well, this one doesn't have a gamma, so this is just the next reward, plus a half of the second reward, plus a quarter of the third reward, plus an eighth, right? So it keeps getting halved and halved and halved each time. So we're discounting it. And so the discounting means that we are going to weight things that are far in the future differently or less than what we're weighting them now. So if we have gamma equal to 0, what happens? Anyone? What will our return be if we set gamma to 0? Yep. So if gamma is 0, what is this term going to be? What are any of the terms going to be? Yeah, so what would so then, now that you know all the gamma terms are going to be 0, what would the return be equal to? 0. Well, we've got one without a gamma, right? So yeah, we figured it out. So if gamma is 0, then the return is just the next reward. So all we care about is the next reward. What you were saying, though, I think, is that if gamma is 1, it's just the same as what we've always been dealing with. Because 1 to the power of anything is just 1. And so if gamma is equal to 1, then we don't discount at all, right? So it's kind of unintuitive, but as the discounting number goes down, we discount more, right? So that's what this is. So if you're watching the video, my face is covering up part of this formula, but that's just the same formula that's right here, so we don't need to necessarily see that. But the discounting rate determines the present value of future rewards. So the reward you get at k time steps in the future is only worth gamma to the power of k minus 1 as if it was the next reward that you were going to receive. So if gamma equals 0, the agent only cares about the next reward because all of those gammas become 0, so all the other things don't matter. And if gamma is 1, then the reward formula is the same as the return that we've been looking for episodic. So as gamma approaches 1, the agent becomes more farsighted, so it weights everything equally. The really cool thing here, though, mathematically, is that this relates current rewards to future rewards. Or, sorry, current returns to future returns. So returns at successive time steps are related in a mathematically important way. So if this is g of t, which is my return following the current time step, and that's equal to this formula, well, let's take a gamma and factor a gamma out of everything from this term onward. So this is what we get. We get gamma times this, but look, if we take this and just increase the t by 1, we get everything that was in here. So that means that the return from this time step is equal to my next reward plus gamma times the return following the next time step. Okay, so what I've done here is I've come up with a formula for my current return. And so this is what this means, okay? If I'm right here at this time step and I want to know what my return is going to be, right? So if I take an action and I'm over here now at the next time step, whatever my return was going to be from here, that's g of t plus 1. So whatever my reward was going from here to there, I'm just adding one term to this return. That's all that says, right? So the thing that I'm going to get from doing this action at this state plus the rest of it. And so this is going to come in handy later when we talk about dynamic programming. Because what it does is instead of having all these terms, we're stating that, oh, the value of doing something at this state is highly related to the values of my neighboring states, right? So we'll look at that in a little bit. Someone asked a question in the last class which talked about episodic versus continuing tasks. So what is an episodic task? An episodic task is a sequence of actions with some sort of terminating state, and these episodes would be considered independent. So for example, a play of the game, or a trip through the maze, or a pathfind, or whatever. And so here, the return is the sum of a finite number of things with an actual terminating state here, or a terminating time, capital T. So we can sum all of these things up. So the object of the agent is to determine a policy which maximizes that expected return. All right, but what is a continuing task then? Well, some tasks don't break down naturally into episodes, right? What if we had a robot we were trying to guide around, or even like real life? I can consider my life, you know, an MDP maybe, and try and solve for some future return. But my life, well, okay, if you want to get really morbid, I guess my life is one episode, but it's really a continuing task, right? I'm just doing stuff. There's no final time step that I want to add everything up for. So the goal, it goes on continuously without any limit. And so, for example, a long lifespan robot or a control task, like some robot in a workshop who's constantly doing stuff and there's no real episodes to it. So the episodic formula doesn't work because we don't have this final time step t anymore, right? So how do we do this? Well, the way we're going to do this is to come up with this unified notation, and all of this is in the book, by the way, if you want more details to study for the exam. So what we're going to do is we're going to modify episodic tasks to become a special case of a continuing task. And how are we going to do that? Well, let's say here our episodic task had 3 states in it. So what we're going to do at the end of that third state is we're going to add another, what they call an absorbing state, that just always loops back on itself and has a reward of 0, right? So by doing this, yeah, it seems a little hacky, but now it lets us use this infinite sum formula for a continuing task to talk about episodic tasks as well. And so what this means is we can use, by modifying episodic tasks in that way, we can just use this one nice unified formula, and we don't have to have some things over here going to infinity, some things over here not going to infinity. So this will apply to episodic tasks as well, if we want them to. Okay, let's revisit action values just a little bit. So recall action values Q of A. So Q of A was the value of doing action A, but we said that the value of a specific action is going to vary depending on the state that it was issued in, right? So for example, moving up is good if your goal is up, but in another state, you might be above the goal. And so moving up would not be as desirable as if you were below the goal. And so what we talked about is, instead of talking about the value of actions, we're going to talk about the value of doing actions at a particular state. So this is QSA is the value of doing action A at state S. So here was the example we looked at. So we have a state, and we have maybe up, down, left, and right as our 4 actions. And based on all the things we did in the previous 2 lectures, we were going to treat every state as one of these bandit problems, right? That's how we were going to solve for those values. So the values QS of A, so this would be the value of being at state S and going up, the value of being at state S and going down, the value of going left, the value of going right, okay? So we get rewards by doing actions at states and ending up at other states. A value is an estimate of how much total reward we expect to get in the future. So remember the difference between an immediate reward that we get and a value, which is an expectation how much reward we're going to get in the future. So rewards depend on a single action, but values depend on a policy, right? Because we don't know what the value is going to be unless we know what we're going to do. And so if I tell you what's the value of being at this state, well, I might be right next to a cliff. So if you choose to walk off the cliff, that's probably going to mean that this value of this state is very low. If you choose to not walk off the cliff, it might be a neutral value, right? So we can really only talk about the value of states if we know the policy that we're going to apply to that state. So this is a new thing that we're introducing now. So we must know what we will do in the future in order to estimate the value of future rewards. So let's look at a pretty funny example here. So say we are at this state S right here. If we go up, we get some sort of power up. That might be pretty good. If we go left, we get the treasure. That's really good. Maybe there's a high reward from that one. If we go to the right, we step into the fire. And if we go down, we run into the dragon, right? So if I were to ask you, what is the value of being at this state? What would you say? Is this a high valued state, neutral, low? What is the value of being at this state? What is V of S? Yep.
Neutral.
Why is it neutral? So the response, just for the mic, was that it's neutral because there's 2 bad options and 2 good options, right? So that's a pretty intuitive thing to say. It's not wrong or right, because what we haven't done is talked about our policy, right? If my policy at this state said to go down, that's a pretty poor valued state. If my policy at this state said to go left, then that is a very high valued state, but with respect to the policy, right? If you're thinking about this as like a sort of a human problem, if whenever I go through a door, I have a 50% chance of winning $1 million or a 50% chance of falling into a fire, is that really a neutral value just because you're taking the average of one of 2 extremes, right? So we've got to make sure that we actually apply a policy to this. So here's another example. I don't know who took this picture, but I found it online, and I'm probably on a list now because I was like Googling babies and stoves and stuff like that. But the reason that this particular state value is really low for a baby versus an adult is because of the policies, right? Babies have not learned as much as adults. So they might still have an exploratory policy, meaning that they haven't learned a lot about what a hot stove is yet. And so one of the, there might be a 20% chance that they pull boiling water down on themselves, and that would be terrible. But an adult would be like, I've been in this situation a bunch of times, I've learned a lot about this, so I am not going to pull this down on myself. So it's very difficult to say what the value of the state is without talking about the policy of the agent who's at that state, okay? Similarly, this is a screenshot from an assignment, and it's colored based on the value. So if it's a brighter color, it has a higher value. And so here, this policy is stating I should go to the left. So it has a higher value because it's pointing toward the goal. But if you look here, this is shaded a little bit darker because the value of going up here is less, right? So it's dependent, the value of the state is dependent on the policy. So what we're going to be talking about from here on is Q of pi. And so this is just adding that pi, the policy, to this value. So overall value only makes sense if we speak about it within the context of a policy. How can we know the value of something if we don't know what we're going to do from there? So Q pi of SA is the expected return starting from state S, taking an action, and then following the policy from there on. So Q pi of SA is the expected value given a policy of the return, given that state, the current state is state S and the current action is action A. And this formula, so what is the return? Well, it's this, right? So these 2 formulas are identical. The expected value of the return, now that we know all the math and we've factored in discounting, is just this summation. And so the important thing to keep in mind here is that the value is going to depend on the policy. So here, V pi, so the 2 different things that we've been talking about is the Q values and the V values. So Q is the value of doing an action at a state, and V is just the value of the state itself. So what is the expected value at being at a given state? Well, it's just this, okay? So it's the same formula as this, but without having taken the action. So Q of SA is saying, what is the value of the current state and taking this particular action and then following the policy, whereas the value of a state is just saying, what's the value of me being at the state and following the policy? Okay, so the MDP problem or objective is to choose a policy pi that maximizes that, okay? And so we're gonna eventually get to how we actually form the policy, but it's important to understand like what this formula is actually saying, and hopefully you're getting that now. So a really cool thing is that this can be mathematically outright solved by dynamic programming if we have a complete model of our environment. Okay, so if we know all the probability distributions and everything, we can use dynamic programming. And dynamic programming, if you remember your algorithms class, is a method of solving a problem by relating the value of a given state by previous states, right? So neighboring states in the problem space. So dynamic programming. So DP is a collection of algorithms that can compute optimal policies given a perfect model of the environment as an MDP. And so the main thing when you're talking about dynamic programming is that my value at a given place is related somehow to the value of my neighbors, right? If I am in a given state and all the states surrounding me are literally on fire, it's probably not good to be at the state that I am at, right? Because it's probably also on fire. So we will use dynamic programming to compute the value function, and then we'll use the value function to compute the policy. Because if I somehow could figure out the value of all my neighboring states, then I'm just going to go to the one that has the highest value, right? If I could go up and get a value of 100 or down and get negative 100, I'm going to choose to go up. Why wouldn't I? So here's an example, a numerical example, wink, wink, exam of dynamic programming to figure out a value. So here, yes, I'm still using grids up, down, left, and right. It's just easy. Don't blame me. So here we go. We're in our like assignment 1 and 2 environment where I have some states. I can go up, down, left, and right. So I've labeled these actions up is 0, down is 1, left is 2, right is 3. That just lets me put these values into an array like we did last time. And so let's say that I know the value of this state is 20. Now, I realize that I've been talking about v of pi so far, right? So pretend that's v of pi. I just forgot to put it there, and it's kind of tricky to fit it all in that little circle. So the value of this state up here is 20. The value of this one is 30. The value of this one is 10. And the value of this one is 0. Okay? So if I had to ask one of you, what is the value of the middle state? What would you reply to that? What do you think it is? Is it going to be bigger than 0, less than 0, 10, 20? Any guesses at all of what the value of the middle state would be? Yep. Maybe the average. Okay? Why would you say it's the average? Not a trick question. I'm not trying to trip you up. Sure. But you're getting to something here. And I like just a couple of slides ago, what do we need in order to figure out the value of a state? The policy, right? So figuring out the value, well, we need to know where we're going to go, right? So we can't say anything really about the value here other than, well, it's probably not going to be negative because none of our surrounding states are going to be negative. So let's have a look. And so what is the probability that we select each of these actions, right? What is the thing called that tells me the probability of selecting actions? The policy. That's literally what the policy does. So let's say that we take a policy that is equiprobable, meaning that equiprobable just means that everything has the same probability, right? I have a 1/4 chance of going up, down, left, or right. So if that's the case, then we would take the average, like you said, because the average here is the sum of everything divided by 4. So we would take the probability of taking action 0 as 1/4, the probability of taking left as a quarter, down as a quarter, and right as a quarter. So if we have a 1/4 chance of getting 20, and a 1/4 chance of getting 30, and a 1/4 chance of getting 10, and a 1/4 chance of getting 0, well, you may say here, okay, let's do this math in our head without having to compute any decimal places. 30 divided by 4. That's not a trivial calculation to do. So here's a little tip for this. If all of the things have the same denominator, add up the numerator and then divide it, right? So if we have 30 plus 20 plus 10 plus 0, what's that? 60 divided by 4? 15. So the value of this state is 15. Why? Because I had an equal chance of getting these to a state with those values. So now, let's go back here. What would be let's do some mental math. What would be the value of the middle state if my policy said 50% of the time go up and 50% of the time go left? Put your hand up if you can calculate that one. And the other two, never do those. Yep. 20? Might be a little bit off. So how did you calculate it? Oh, sorry, I said up.
Oh.
Yeah, did I say right or did I say up? Okay, so up or left? I know you know how to do the math, so what is it now? Yeah, so it would be 30 divided by 2 plus 20 divided by 2, which is 25, right? What is my value of this state if I always go to the right? 10, right? Because I'm always going to the right. I'm never considering any of the other things. So this is the main idea behind this. You look at the policy, whatever the policy says to do, you take the probability of taking the actions, look at the value of the neighboring states, and then sum that up. That's pretty easy. All right, so let's do a more real-world example. If this is my current state, what is the value of being at this state? What is it dependent on? The policy, right? Because this person, for this person who I guess, you know, and this is, unless this is the last picture ever taken of them, probably has a pretty good policy when it comes to unicycling, right? So let's simplify that policy a little bit into like the probability of going to one state or the other state. So let's say that there's a 90% chance of going to the safe state after this state, like backing up off of the cliff, and you get a reward of 10 because it was a little bit thrilling or something like that. So you get some positive reward from taking this dangerous action. Then you look at, okay, there was a 10% chance of actually falling over the cliff, right? So what is the value of the current state using what we currently know about dynamic programming? Well, it would be 10% of this plus 90% of this, right? So we'd get this very negative value for being in this state. But if this person had a very, very, very good policy that 99.999% got them safe, maybe then yes, there would be some, like on expectation, this would just be a little bit thrilling thing to do. Now, I'm not saying that you should apply this formula when you go out to do daredevil stuff, right? Please don't try this at home because Dave said if the formula works out, you're going to be okay. No, I'm just trying to give you like a funnier real world example of that. So it turns out that this is all done using something called the Bellman equation. Has anyone seen the Bellman equation before? Yeah, it's not probably wouldn't have seen it, but this is the big honkin' Bellman equation. And it looks a bit scary at first. I was a bit scared when I first saw it, but it turns out it just said exactly what we were talking about. It's just now it's in mathematical form instead of English form. So let's compute the state value function v prime for an arbitrary policy pi, not v prime, v pi. And so we're going to use the Bellman equation. And v pi of s, that's what we were just trying to calculate. And this is what we were trying to do, okay? So let's have a look at this formula. Here, we're looping over all of the different actions, right? So pi of SA is the probability of taking A in state S under policy pi. That's a tongue twister. So what this is, that's the 1/4 or the 1/2, right? So we loop over all the actions and we say, what is the probability of taking this action at this state given the policy? So for that very first example, all of this term is going to be 1/4. For the second one, for the up action and the left action, it would be 0.5. For the right action and the down action, it would be 0. And for the other example, this one is 0 for everything except it would be 1 for going to the right. Okay, so this just says loop over all the actions and determine the probability of taking that action at that state. This term here is a little bit tricky. This is, if this were a deterministic environment, then this term would always be 1. Because this term says, what is the probability that taking action A in state S transitions me to state S prime? And we loop over all of these, right? So this means if I'm at a particular state, what are all the potential states that I could go to from this state by taking action A. So for an example, if we were playing blackjack, this would have 3 different values. Well, there'd be 3 different states that we can get to from any action that we take in blackjack, right? We could either take an action and win, take an action, lose, take an action and draw. So what is the probability that hitting with 20 brings me to winning? What is the probability that hitting with 20 brings me to losing? What is the problem that hitting with 20 brings me to drawing? Right? So that's what this term means. But in a lot of cases, this is just going to be 1. If the environment is deterministic, then that term completely goes away. Now, 2 things that this equation introduces that our examples did not have, because I wanted to keep it simple at first, is first, there's actually a reward that happens from doing this action at this state, right? So if I go back here at this, we're not just summing up all of those values in the Bellman equation. We're first adding the value of the reward that we get from doing that action. I just wanted to keep it simple, right? So here, if we were doing this with the Bellman equation, this would be a deterministic environment, so that middle term would always be 1. We did not get a reward, so that reward would have been 0. And here, the gamma value was 1, because we didn't do any discounting on the next thing, right? So in the Bellman equation, we have room here to add the value of the reward that we got from actually taking that first action, plus gamma, which is the discounting factor, then multiply that by the value of the next state given the policy. Okay, so that's not so bad. Here's that formula again. And what we're going to do is say, okay, most of the time we have these deterministic environments. So in the case of actions deterministically transitioning things to each other, this is a much more reasonable, understandable version of that algorithm. So I don't know about you, but I still prefer to look at things in terms of code instead of math formulae. That's just how my brain operates. So here's the formula up there. Let's turn that into code. So if v of s, this is the current value of s. Now this is given a policy, but we're just going to make our variable in our code v. P of sa, that's going to store the 2D array here. Policy is what is the probability of doing action A at state S, right? So if we go back to this example, then our P array is going to be of length, or P of this state is going to have 4 values, and they're all going to be 0.25, right? Because that's our probability of taking everything. And then for each state in the environment, let's say we wanted to apply this to each of the states. You could do it to one or every one of them. Now, this is going to be a summation looping over every possible action, right? So what I'm going to do is initially set the sum to 0, because if the sum, I haven't iterated over it yet, I'm adding things up. Let's start at 0. So for each legal action A at state S, which is what this says, loop over all of the actions at state S, PR, that is the probability of choosing A at S, which is just equal to P of SA, right? I've already got P of S. I know what state I'm at right here. And then for each legal action A, okay, so I've got S, I've got A, here's the probability. So in that case, it was a quarter. I figure out what the environment's going to tell me what the reward is from doing action A at state S. S prime is the next state if I apply the action to the current state. And then I have everything I need for this formula. So since I'm summing up, because this is a summation, I take V of S and I add to it the probability right here times the things in here, which is the reward plus gamma times V of S prime. Okay, so to me, this makes a lot more sense than the mathematical formula because it tells me step by step all the things in sequence that I have to do. All right, so now that we know that, how would we update the policy, right? Because we're figuring out the value, but really what reinforcement learning is all about is figuring out a policy. And it's simply take the thing that has the highest value. That's it. If we know the values of all the neighboring states, then the thing I want to do is go to the neighboring, the one that the highest value. So we just computed that. If we want to know the value of doing an action at state S, then look up the value of the resulting state. That's it. So what we do is that pi prime, again, prime meaning the next one, so the next iteration of our policy, pi prime of s, it's just going to be the action that maximizes Q of SA, right? That's it. So if I figured out the value of all my corresponding states, then Q of SA is going to be related to those values, and I'm just going to take the action that maximizes that value. So here's the policy update in code. Now, let me just go back here for a second to illustrate something. Sometimes what you'll do for your policy is you'll say, okay, here, let's just say they were, let's say it's like this. So if I was updating my policy now, what would my policy be? It would be to go left, right? Because going left has the highest value, right? So what I would do is in my P of SA, I would set P of left to 1 and all the other ones to 0. So I'm making a probability distribution of all of those actions. So up would have probability 0, right would have probability 0, down probability 0, left probability 100 or 1. Let's say now, for sake of argument, that up and left were both 30. Okay? So typically, what we do in our policy, if there are ties, is in order to keep exploring both of those as we keep training or whatever, we're going to say, instead of just choosing one of them to do, we're going to say, with equal probability, choose every max action with equal probability. Okay? So if there would be two 30s here, we would say go left with 50% probability, so 0.5, go up 0.5, go right 0, go down 0. Okay? So if there are multiple maximums, we want our policy to say choose each of them with an equal probability, depending on how many there are. So if they were all the same, we would choose each action with a quarter probability. All right, let's get back to this formula. So here's the policy update. So I know this is a little bit small, apologies for that. I wanted to fit it all on a slide. So P of SA, that is the probability of choosing A at S. Max, I'm going to introduce a couple of variables here. Max A, in order to keep things short, the full name of this should probably be the actions that maximized the value. Okay? So what this is going to end up being is an array of actions that gave me the highest value. So if there was only one maximum, then the array is going to contain the action that made this maximum. If there are multiple maximums, then let's say if there's 3 maximums, this array is going to be of size 3 and contain all the actions that led me to that same maximum. Then since I'm taking the max of something, I'm going to be comparing to negative infinity just to keep that value. Then for each legal action A at state S, so I look over all the actions, I'm going to get to the next state by applying A to S, and then I'm going to say, okay, there's a couple of things here. Either I have some value already in that max array, or I don't already have some values in that max array. So this is basically saying, okay, this is the first one, right? So if this is the first one that I've done, I know that I have a new maximum, right? Because it's going to be bigger than negative infinity. So this just says, okay, if this is the first action that I'm looking at, then I'm going to push this into the array, because this is a new maximum, and so the maximum should go into the array. And I'm going to set my maximum value equal to the value of that state. Right? So this is the case where this is the very first value that I'm looking at. Now, for each subsequent action, there are going to be 3 possibilities, and I'll talk about those possibilities in a second. So, if there is already a value in this array, that's what this is saying, right? So if it was empty, do this. Otherwise, there's 3 things. The 3 things are either this new value is bigger than the things that are in the array, it's the same as the things in the array, or it's less than the things in the array. And we want to do something slightly different in all of those cases. So if the value that we just got is equal to our maximum value, then this means, oh, this action also takes me to a maximum action. So I'm just going to add this to the array, right? So if my first action gave me a value of 100, then action 1 is going to be in there. If action 2 also gave me the value of 100, and it's the same, then I'm going to just add this action into that array, because now I have two things that gave me the maximum action. But if this new value is strictly bigger, so if this is a new true maximum and it's not the same size, then what I have to do is, okay, these things in the array are no longer the things that give me the maximum action, right? So I clear out the array, then I push this action in, and then I set the maximum value. So if the next thing after I had two 100s was a 150, then I'm going to take that action and that should be the only thing in the array, right? Does that make a bit of sense? I'll show a numerical example in a second. And in the other case, where it's less, well, we don't care about things that aren't maximums, and so we just do nothing here, okay? A question or a stretch? No, you don't have to put your hand down, I was just curious. And then we actually have to update the probabilities in our policy array. So for each action A at S, if A is in this maximum array, then the probability of taking that action should be 1 divided by the number of maximums, right? And otherwise, if it's not, then the probability is 0. And I'll show an example of this in a second. And so you update the policy to have an equiprobable chance of selecting from all actions with max value and 0 otherwise. All right, the example I think makes this very clear. Let's say we have 5 actions that are possible from a given state, A1 through A5, and those yield the new states S1 through S5, and those states have values 10, 0, 10, 5, and 10. So if we look here, we have 3 maximums, right? So the actions that maximize the value are actions A1, A3, and A5. So that means our new policy, we want to equiprobably select from actions A1, A3, and A5 because they led us to maximums. And otherwise, all the other actions are going to be zeros. So our new policy is going to be 0.333, repeating 0, 1/3, 0, 1/3. So does that make sense? So we just take we look at the values in the surrounding cells, we see what the maximum is. If any of the actions produce that maximum, then we choose them all with equal probability. Otherwise, we don't want to choose the thing. So what we've just seen is we found a value and then we updated the policy. And what updating the optimal policy involves is going to take these 2 steps and then repeat them for some number of iterations. So first, we update the value estimates based on the policy. And second, we update the policy to choose the actions which lead us to maximum valued states. So this is the loop that we showed in the beginning. We have an agent, but I've added this pi here now, right? Because it doesn't make sense to talk about values if we don't have a policy. So the agent has some policy. It's going to take an action based on that policy, which is going to transition the environment into a new state, and the environment is going to give us a reward. We look at the state and the reward we got from transitioning from that state by that action to this state at the reward. Now we recalculate the values based on that reward that we got, and then the cycle continues. Oh, and then we update our policy based on those new values. So it's like update the values, take an action, update the policy. Take an action, look at the values, update the policy. So just keep in mind that, let me go back here to the Bellman equation. I meant to put a slide in on this and I forgot. So you might think that all of reinforcement learning is just applying the Bellman equation, right? But the trick here is that these values are in practice very difficult to figure out, right? Even if we have a model of our environment that can perfectly transition us, like for example, it's pretty easy to write a blackjack simulator. If you get an ace, add 1 or 11 depending on this. If you get a 3, if it's over 21, you lose, etc. It's very easy to write a model of blackjack. But if I ask you, what's the probability of going from this state of blackjack, taking this action and ending up in another state. That's actually a much harder question to ask, or to answer. And the reason is because you might have to try all of the actions a bunch of times. It might be a stationary distribution. It might be a non-stationary distribution. And so this is the reason here that in practice, we cannot apply dynamic programming to reinforcement learning problems. Okay? If it's a deterministic environment, a finite state space, yes, it would be pretty easy to just outright solve the problem with a Bellman equation. But in practice, it's not. So the Bellman equation, it lays out the mathematical foundation for solving this problem, but it is not directly applicable all the time in this way. So yes, because we don't know those probabilities for most environments, we are going to have to experiment and try actions, etc., in order to figure out values, rather than just looking at our neighboring states and knowing these probabilities. Okay, so now that we've seen this, just a couple of exam questions that you could get on this. So action value versus state value. So that's the Q versus V. What do they mean? MDP properties, so the SAPRI stuff, the definition of the Markov property. If I gave you an example of a game, is this Markov, is it not Markov, or come up with an example of a game that is non-Markov. Dynamic programming, example calculation. So that thing where I showed you the up, down, left, and right, and you had to calculate the value of the state given those other things. So that would be using the Bellman equation. So giving the neighboring values, the value of the reward, the value of gamma, calculate that. A policy update. So if I say, okay, here are the values of doing the actions at this state, meaning if I gave you literally this slide, you would have to calculate this value down here. Okay. And also any combination of those previous two. Meaning like any combination of calculating values and then updating the policy.